Okay, so good morning, everyone, or good afternoon, depending on where you are. My name's Katrina, so I'm the machine learning math lead here at Cohere Labs. So this session is a Q&A session. So this is a little bit different from our typical ML math session. This is following up our initial machine learning math refresher that we had as part of ML Summer School. So our first session was on July 2nd, so you can see the recording of that. And since then, I've had lots of questions so I've kind of compiled the Q&A and have some answers for you today. So the format is a little bit different from normal ML math sessions. So this one, I actually have a slide deck. There's a little bit more theory than a normal math session. So we're going to just go through some definitions on the slides, and then I'm also going to take you through some examples that we can work through together. And my typical machine learning math sessions will usually just be on the whiteboard the whole time, kind of going through problems. So yeah, I hope you enjoy our session. Okay, so today what we're going to go through, we're going to start by looking at different norms. So the L0, L1, L2 norm and their applications in machine learning. The second thing we're going to look at is eigenvalues and eigenvectors. So last time we had to rush a little bit at the end. We didn't quite have enough time. So we're going to go through eigenvalues and eigenvectors in a little bit more detail and kind of talk about their various applications in machine learning beyond just principal component analysis. And then we'll also look at loss functions and how there's various different types of loss functions. And we're going to understand the mathematical equations behind all these loss functions. And at the end, if there's additional time, we'll go through some Q&A. Okay, so the first thing I just want to let everyone know is I do have the Math and Machine Learning YouTube channel. So all the topics that we cover today are also covered in great detail on this channel. So I will send the link to the channel in our chat right now. That way everyone can access it. There's over 160 videos right now. So they're a great resource for all of you if you want to learn more about the math behind everything. And okay, so our first question of the day is really how to calculate the L0 and L2 norm and when are they used. So I'll show you a slide, talk about some definitions, and then after that we'll switch to a whiteboard and kind of look at some examples there. So the L0 norm is a bit of a funny case because it's not actually a real norm. It doesn't satisfy all the conditions of a norm. So the L0 norm of a vector just counts the number of its non-zero elements. So if you were to have, for example, 0 to 5, your L0 norm would be 2 because you have 2 non-zero elements, and we'll look at more examples in a moment. So the use cases. So the L0 norm is primarily used for sparsity inducing regularization. So what that means is that it encourages models to have fewer non-zero parameters, which can lead to more interpretable models, and it can also reduce computational costs. So you're trying to really have fewer non-zero parameters. It helps sometimes in feature selection as well. So the big challenge here with the L0 norm is that it is non-differentiable. So that makes it computationally challenging to optimize directly, because since it is non-differentiable, then you can't usually apply your regular optimization techniques. You can't use gradient descent because it is non-differentiable. So some examples of when we would use this be in, sorry, I'm just trying to let everyone into this call. Here we go. Some examples when we would use this would be in feature selection. This is a huge one. Oftentimes in machine learning, you have various different parameters, different features that you're trying to use, and that can make things very computationally heavy. So in feature selection, the L0 norm can be used to identify what are the most relevant features by penalizing models that use too many features. So it really tries to narrow it down. It also used in sparse neural networks. So the L0 regularization can be applied to neural networks to prune the connections, making the network smaller and more efficient. And then finally, you can use compressed, it's also used for compressed sensing. So in compressed sensing, the L0 norm is used to reconstruct sparse signals from incomplete data. So those are just some different examples in kind of machine learning where we see it. So I'm going to switch over to a whiteboard for a moment, and then we can just kind of go through some examples together. Okay, so here looking at the L0 versus the L2 norm, if we kind of go through examples here, this first one here, like we said, the L0 norm is when we're counting all of the non-zero elements. So it's actually just from a mathematical stance, pretty easy just to calculate. So we just go through and look at all your non-zero elements. So in this example, your L0 norm would equal to 4. If you had something with like many zeros and only like one other number, then over here, your L0 norm would just equal to 1 because you only have one non-zero element. So again, this one is often used to, for feature selection because we're focusing on the non-zero values here. And by hand, it's quite simple to calculate, but it's difficult to optimize because it is not differentiable. Okay, so let's move on to the L2 norm over here. So the L2 norm, I'm pretty sure a lot of you are actually familiar with. It's also known as the Euclidean norm. So the L2 norm of a vector is the square root of the sum of the square of its elements, so known as the Euclidean norm. So this is the one when by default, if someone asks you to find the magnitude of a vector, this would usually be the default one that one would use. So the L2 norm is widely used for regularization in various machine learning algorithms, and it really helps prevent overfitting. And overfitting is a massive issue in machine learning because then your problem does not generalize well to other problems. So that's always a big thing when we're doing machine learning problems is how can we balance having an accurate model? So we're balancing accuracy with generalization. So if a model is overfitting, then it's not generalized. That means if you have new data that the model has never seen before, then it doesn't know how to do a proper prediction. So the L2 norm really comes in these use cases to help prevent such overfitting. And it also helps us to smooth out our decision boundaries and improve generalization. So the big advantage to this one, and the reason why it's so commonly used, is because it is differentiable. We like it when things are differentiable because that means we can optimize them, which is amazing for us. So by being differentiable, it makes it easier, again, to optimize using gradient-based models, which is a very commonly used model, especially in when we're dealing with neural networks and language models. So some examples in machine learning when we would use the L2 norm is ridge regression. So this uses the L2 regularization to shrink the coefficients of less important features towards 0 to prevent the overfitting. So that's very helpful for us. So it's able to smooth out kind of all the parameters, and the parameters that are less important, they're going to shrink, and then that prevents us from overfitting the general model. So in neural networks is another example. So this norm is used to penalize large weights, leading to more robust models. And in support vector machines, which is often used for classification, the L2 norm is often used to control the margin and prevent overfitting. So it helps smooth that decision barrier that you would have between your different categories of your data. So that's where that one is used. So let's take a moment and look at a whiteboard here, and we'll practice calculating the L2 norm. Okay, everyone should be able to see that now. Okay, so for our L2 norm, let's take just a simpler example to begin with, and let's look at a two-dimensional array. So we have a 2D vector. Let's say our vector A equals to 3 and 4. So this is a two-dimensional Cartesian vector, and we're looking to find the L2 norm. So what we can do is let's just write out a general equation for this. So say A equals to x and y. So these are our kind of two components of our two-dimensional vector. So if we were to go and then for the, So if we were to go and look for the 2 norm, so one way how we would write this is we put the absolute value signs around our vector A, and then in subscript at the bottom we'd have a 2, because there's various different types of norms. Like you saw, we have the L0 norm, L1 norm, infinity norm. So this is the 2 norm. So like we said in our slide, we take the square root of each element squared, and then we add them together. So this also should look very similar to Pythagorean's theorem, because you're just essentially finding the hypotenuse of a triangle, especially in 2 dimensions. This is easier to see. So now that we have this definition, let's apply it to our example over here. So if we take our vector A over here, and we're looking for the 2 norm of it, we just have to input our values. So we're going to take the square root of 3 squared plus 4 squared. So as a result, we just have the square root of 9 plus 16, which equals the root of 25, which equals to 5. So if we were to think about geometrically, how does this look? It's great because we're only in 2 dimensions, so we can actually take a peek at this. So again, A was 3, 4. So this actually is a good review of Cartesian vectors as well. So this 3, again, represents our x component, and this 4 represents our y component. So if we look at our xy plane over here, we're going to move over 3 spots on our x. So 1, 2, 3. So we're over here, which is 3. And then we're moving 4 spots for our y. So we go 1, 2, 3, 4, and this would be our y. And then when we find our vector, what we're doing for the 2 norm is we're taking the shortest distance to go from the initial point to our end point. So from here, we'll start at the origin, and then we're going to draw a vector to our final point over there, and that's our vector over here, 3, 4. So again, this is the most popular norm, and it's the shortest distance to go from one point to the other point. So it's also great. You can kind of understand vectors, and this would be considered your displacement vector if you're going in that angle. And then again, we can see that this one would then have a magnitude or 2 norm of 5, which we just calculated. And then this can be applied in further dimensions. You would just continuously take the sum. So if we had a larger vector, for example, we'll just say vector B equals to x, y, or we can call it x1, x2, x3, all the way to xn. We would take then the L2 norm of B, and we would follow the same thing. So we would have the square root of square of x1 plus x2 squared all the way to xn squared. So you can see that this formula can be generalized and applied to the nth dimension, which is really great for us. Okay, so that is kind of the end of our discussion on L0 and L2 norms. So we're going to move on and talk about our next topic. The next thing we're going to look at, a common question that I had, was how to calculate eigenvalues and eigenvectors, and when are they used in machine learning. So I'll give you some ideas of when they're used in machine learning on these slides, and then after that, we're going to go back to the whiteboard and we're going to solve together how to actually find eigenvalues and vectors of 2-dimensional matrices. So principal component analysis is the main way that eigenvalues and vectors are used. So in my Q&A questions, I had a lot of people ask, well, what are applications beyond principal component analysis? But those of you who are new to this, let's just take a moment and look at what PCA is. So essentially, the main reason why we use PCA is for dimensionality reduction, and this leverages our eigenvalues and vectors. So PCA helps by identifying the principal components, which are known as the eigenvectors, of the data's covariance matrix, and this represents the directions of maximum variance. So essentially, this eigenvector that corresponds to our biggest eigenvalue is the vector or the component that's going to capture the most variance within our data. So if we had to approximate a problem, say we had 100 dimensions and we only wanted one dimension, we would then choose the dimension that has the most information about our data because we want to preserve as much as possible. And that's what this first principal component does for us. So by selecting the principal with the highest eigenvalues, PCA effectively can reduce the dimensionality of the data and preserve most of its variance. So the reason why we would do this is because sometimes we have problems that have thousands of dimensions, which makes it very computationally expensive. So by reducing the dimensions, it allows for more efficiency. So we'd also have quicker problems. So that's why it's often used in machine learning. So let's move on to a second one. So another related reason is for data transformation and feature extraction. So eigenvalues and eigenvectors are essentially described, you'll see later, as linear transformations of data. So these eigenvectors can be used then to transform data into a new coordinate system where the data is better structured and easier to analyze. So this transformation is really neat because it can reveal hidden patterns and relationships within the data, making it easier to extract meaningful features. So imagine you have a problem and you're in like the fifth dimension. This is really hard for our brains to understand because we can only see up into the third dimension. But when you're trying to visualize your problem, like say you're coding in Python, you're only limited to that 2D or 3D plane. So for example, you might decide to take two of the coordinate systems. Maybe you take the XW coordinate system and just look at that. You might not be able to see a meaningful relationship within your data. But if you were then to transform it and look at it from a different perspective, you might actually be able to find a really neat linear or exponential relationship within your data. So a lot of this is about perspective, and understanding eigenvalues and eigenvectors allows us sometimes to transform our data and look at our data from a new perspective where we can actually find new hidden patterns. So that's a very meaningful aspect and application of eigenvalues. Another question that I had was, well, how are eigenvalues and eigenvectors used in modern transformer models? Because as we all know, transformer models are what's really leading our AI right now. Everything's based off of large language models, these huge networks, transformer models, autoregressive models. So how are eigenvalues used within them? So there's four main areas where they're used. There's definitely much more, but I'm going to talk about the four main ones that I find very pertinent. So the first one would be analyzing the attention mechanism. So the attention mechanism in transformer models relies on matrices. Pretty much everything these days relies on matrices and our numbers, right? So eigenvalues and eigenvectors of these attention matrices can reveal insights into how the model attends to different parts of the input sequence. So again, that allows us to peer into our attention mechanism, which is really the basis for these transformer models. Secondly, eigenvalues and vectors can help understand model capacity. So by examining them, researchers can assess the model's ability to capture hierarchical relationships within the data and potentially identify areas where the model might struggle. So this is important because sometimes when you're going into a model, it's good to understand the strengths and weaknesses of your model and understanding areas where the model might struggle. So if you can get a hierarchical relationship within your data, this will help you analyze kind of the strengths and weaknesses of your model, so then you know kind of which area to look out for and which area to tackle during your training. It also has a potential for optimization. So understanding the eigenvalue spectrum of an attention matrix can help identify potential issues like variance distortion or instability, which can lead to hallucinations. So for those of you who don't know, hallucinations are basically when models generate incorrect or nonsensical outputs. So understanding your eigenvalues and vectors can actually help you identify these issues, which could lead to hallucinations. And hallucinations are a big problem for language models, so this is great. It helps you tighten the reins on your models and prevent these hallucinations. And the last point I put out here is that they can help for feature importance. So eigenvectors can be used to identify important features or dimensions in the data that the model is focusing in on. So that kind of relates to our principal component analysis. Eigenvectors can help us identify, or eigenvalues help us identify our principal components. And then once you know these principal components, those can represent important features in your data. So it really helps you kind of tune your attention on what features to look at, and kind of which dimensions of your data are most important. I just got a question. What do you mean by hierarchical relationships within the data? So hierarchical relationships within the data is also, you can kind of think of that as the importance. So when you're training models, you'll have various different features and various different variables. Variables, features, interchangeable. So when you train them, some features will be more important than other features in terms of when you're trying to create a prediction. So that if you think about a simple regression, you'll have different weights on each of your features, and each of these weights kind of represents a different level of importance for the model. So this helps you determine and capture these relationships within the data. So which data might be more important than other aspects of the data, and that helps for predictions as well. Okay, so let's move on to the next one. So just some other final applications before we move on to the computational side is spectral clustering is a huge application. So eigenvalues and vectors of a similarity matrix are used to group data points into clusters based off their inherent structure. So that's a big thing, because a lot of times in unsupervised problems, we don't have labeled data, right? So we have unlabeled data, and we're trying to understand different ways how to group data together. So if we're able to, based off of inherent structure, then that will provide essentially more accurate predictions going forward. This is another really neat application that I found is Eigenfaces for face recognition. So here, this is a very, applicable side of eigenvectors. We can see that eigenvectors of a set of face images, known as eigenfaces, are used to project new face images into a lower dimensional space, enabling efficient face recognition. So you can see directly how you can use eigenvalues in a very applicable side. And lastly, there's linear discriminant analysis, known as LDA. So eigenvectors are used to find the directions that best separate different classes in supervised learning tasks. So again, that goes back to your principal component analysis. It basically separates your data and which direction should we separate our data in to have the best, decision barriers here. So now we're going to go and work on the math. So now that you know how eigenvalues can be applied, let's just look at an example where we can solve these mathematically. Start with just an example over here. So we have a matrix A equals to 2, 0, 0, 2. So technically, we can actually find the eigenvalues right away by looking at this matrix because it is diagonal, but I wanted to take you through all of the steps so you can understand how to find eigenvalues and the related eigenvectors. And we're also going to have a bit of a discussion on algebraic versus geometric multiplicity, because understanding algebraic and geometric multiplicity helps you understand more theoretical parts of linear algebra and linear algebra theory, which will help you understand matrix diagonalization, which is important, again, for machine learning. So in general, if we're looking for the eigenvalues of a matrix, we use this equation. We use the determinant and then of A minus lambda I. So this, and we set that equal to 0. So we're going to take a second and kind of annotate this equation so we know what everything is. Okay. Got a lot of people joining here. Okay. So here we have our A is our square matrix that we have over here. Square matrix. Lambda over here represents our eigenvalue. So this is a scalar value. And I over here is our identity matrix. So identity matrix, known as your ID matrix, essentially this means that you have ones on your diagonal and zeros everywhere else. And note that your identity matrix has to be the same size of matrix A. And over here, let's take a moment and just learn what the determinant is for a 2x2 matrix. So we'll take a moment to calculate that. So say for our matrix A, we have our generic terms A, B, C, D. In order to find the determinant of a 2x2 matrix, we take one diagonal, multiply it together, and then subtract our other diagonal. So in this case, we have AD minus BC. Taking the determinant of 3x3 matrices is a little bit more complicated and requires something known as Laplace expansion. If you want to know how to do this, I do have a YouTube video already out on my channel, Math Unlocked with Katrina, where I go through how to find the determinant of a 3x3 matrix. So definitely check that out, but I don't think we have enough time today to go through all that. So now that we have this equation here for our determinant, we can go ahead and solve the determinant for our matrix A. So we would write that, so we have here that of A minus lambda I equals to 0. So we first now have to find what is A minus lambda I. So that is our next thing. So we have our matrix A, which is 2, 0, 0, 2. And then we do minus lambda times I. And remember, our identity matrix looks like this, and we set that equal to 0. So here we're going to do two skills. We're going to do scalar multiplication and also matrix subtraction. So we're going to multiply this lambda into our matrix and then do matrix subtraction. So as a result, we end up with 2 minus lambda, 0, 0, and 2 minus lambda, and we're setting this equal to 0. So now that we have A, so this part over here represents A minus lambda I. So now what we have to do is take the determinant of this new matrix using our determinant formula, which we showed above. So we'd have to take our first diagonal. So here we've got 2 minus lambda times 2 minus lambda, and then we're going to subtract this product of our other diagonal, minus 0 equals to 0. So we can simplify this right away. So we have 2 minus lambda, 2 minus lambda, and that equals to 0. So this also involves understanding how to factor sometimes quadratic or cubic or quartic equations, depending on how many dimensions your initial matrix is. In this case, by having 0 over here, this does help simplify the problem for us. And because it turns out that is already automatically factored, which is really lovely. So what we do once this is set to 0 is we look at each of these terms individually and set them equal to 0 to solve for our lambda. So what we get is that lambda 1 equals to 2, and then we also get that lambda 2 equals to 2. So now let's take a moment and talk about algebraic multiplicity. So algebraic multiplicity of an eigenvalue is the amount of times that an eigenvalue appears as the root of a characteristic polynomial. So this here, after we do our determinant, this is called our characteristic equation or characteristic polynomial. So how many times is our eigenvalue the root of this characteristic polynomial? Well, in this case, it's interesting because we see that we have the same eigenvalue is repeated twice. So that means that the algebraic multiplicity is equal to 2 because our eigenvalue appears twice as the root of the characteristic equation. So we're going to revisit this in a second when we look at geometric multiplicity. But just for now, keep in the back of your mind that algebraic multiplicity is 2. So now that we've found the eigenvalues, what we have to do is find the corresponding eigenvectors to these eigenvalues. So now I'm just going to use the short form of E and vectors. So this means we're looking now for the eigenvectors. So when you're searching for eigenvectors, you have to look for the eigenvector associated with each of your eigenvalues. In this case, we have a repeated eigenvalue, so we can only look for the eigenvector associated with lambda equals to 2. And we're going to use a special equation for this. So the relationship is as follows. You have A times V equals to lambda times V. So let's again annotate everything that we have. So again, A is our square matrix. Lambda, like we said, is our eigenvalue, which is a scalar value. And this here, which is new, or V, represents our eigenvector. So this equation actually really helps us understand the relationship between eigenvalues, matrices, and eigenvectors. So it shows us that the linear transformation that matrix A imposes on our eigenvalue V is equivalent to the scalar multiplication of our eigenvalue on our eigenvector. So this one scalar value can represent the entire linear transformation of a matrix on a vector. So it will tell us how much this linear transformation has either shrunk, expanded, rotated, scaled our eigenvector. So from a purely linear algebra side, we can see how this one matrix has impacted our vector solely by looking at its one eigenvalue or one scalar value. So this one eigenvalue has so much information. So we've already seen from the slides that it has various applications in machine learning, but from a purely mathematical perspective, from linear transformations, this is what's going on. So in order to calculate our eigenvectors, we actually have to go ahead and rearrange our equation. So like everything in math, whenever we want to solve for something, the first step is to set your equation equal to 0. So if we do that, we've got AV minus lambda V equals to 0. And those of you who are new to vectors, this little hat on top of the V is the vector arrow, so that represents that V is a vector, meaning it has both a magnitude and a direction. So now that we have our equation set to 0, we're going to factor out our eigenvector. So as a result, we end up with matrix A minus lambda times our eigenvector, and that set that equal to 0. So in this case, like I said before, we have a specific eigenvector associated with each of our eigenvalues. So we're going to start by just looking at our first eigenvalue over here, which is equal to 2. So our case that we're considering is lambda 1 equals to 2. And we're going to call this V1 here and lambda 1 right over there. And we're going to start to fill this in. So if you recall, our matrix A is 2, 0, 0, 2. And then we're subtracting lambda. So we minus our lambda right over here. And then the other thing we're going to do right now is we're going to re-represent V1. So we're going to take this for a second and say that V1 here equals to this vector of V1, 1 and V2, 1. Okay? That way we can represent it in its decomposed form, and that will help us when we're trying to do matrix multiplication. So now we have over here V1, 1, V2, 1, and we're going to set that equal to 0. So now this is another skill that you're going to learn, which is matrix multiplication. So matrix multiplication cannot always be performed. That's really important. Certain conditions about the dimensionality of each matrix have to be met in order for this matrix multiplication to be valid. So in particular here, the number of columns, has to equal to the number of rows in your second one. So here we can see that the number of columns equals to 2, and the number of rows of this vector equals to 2. So since they are indeed equal, that means that our conditions are met and we can go forth with our matrix multiplication. So before we go forward, let's fill in our value for our lambda. So here we have 2 minus 2, 0, 0, and 2 minus 2 multiplied by v11, v21, and that will set to 0. So this ends up being a very interesting case for us. We now have a matrix of all zeros multiplied by v11, v21 equals to 0. So if we go ahead and perform our matrix multiplication, what do we end up with? 0v11 plus 0v21 equals to 0, and then 0v11 plus 0v21 equals to 0. So here we have a system. So in order to solve this system, we have to kind of think for a second, because it looks like we just have 0 equals to 0 and 0 equals to 0 over here. So what this means is, you might think, oh, we have no solution, but in fact, it's the opposite. That means that any value of v11 works, and also any value of v21 also works. Pardon me. So as a result, our two eigenvectors, we have 1, 0, so any scalar plus any scalar of 0, 1, where k is a scalar. And that's what we have here, because we said any value of v11. So v11 is represented by this component, and then any value for v21, and that's represented by that component over there. So we now have this linear combination of these two independent eigenvectors. So that's the big thing over here. So we can say that, so this is our v1 equals to this linear combination. So what's happening here? We now want to look at what's called the eigenspace. Oops, did we have someone join? Okay, there we go. So what we're doing here is we're looking at the eigenspace. So the eigenspace is the dimension, basically the number of independent eigenvectors associated with an eigenvalue. So we have eigenvalue 1 equals to 2, and it has two independent eigenvectors associated with it, because we can say that the eigenspace that it spans is 1, 0, 0, 1. So the dimension of our eigenspace, so the dimension of our eigenspace here, space equals to 2. So that's pretty neat. And what that means, the result from that, is that we have a geometric multiplicity. Just write this out for you. Multiplicity is equal to 2. So previously we talked about algebraic multiplicity. That was the number of times an eigenvalue appears as a root of a characteristic equation, where the geometric multiplicity is how many independent eigenvectors are associated with an eigenvalue, or it can also be known as what is the dimension of the eigenspace corresponding to that eigenvalue. And we can see that it equals to 2. So this is the interesting part of the discussion. So I'll just abbreviate it to AM, meaning algebraic multiplicity, and GM, meaning geometric multiplicity. So algebraic multiplicity is always greater or equal to geometric multiplicity. However, if algebraic multiplicity is actually equal to geometric multiplicity, that means that your matrix is diagonalizable. So in this case, we can see that we can get a diagonal matrix because our algebraic multiplicity equals our geometric multiplicity. So here we can get a diagonal matrix. However, if we have that algebraic multiplicity is greater than geometric multiplicity, what that means is that your matrix is not diagonalizable, and it also means that you have a defective eigenvalue. Defective eigenvalue or a defective matrix, because that means that you don't have basically, if you have an algebraic multiplicity of 2, for example, that means that you would only have a geometric multiplicity of 1. So you don't have, I guess, a corresponding independent eigenvector to each of your repeated eigenvalues. So that's quite an interesting discussion on understanding really the theory behind some linear algebra and understanding deeper what eigenvalues and eigenvectors mean, as well as their implications. So definitely go back and consult the slides that we have so you can see all the machine learning applications, but this is a really good start for you to understand kind of how to calculate it mathematically, because as you can see here, even just doing a 2x2 matrix has given you so much I guess, mathematical insight behind this problem. So we're going to go to our last topic over here, which we're just going to do a brief discussion on some loss functions because someone had asked about that. So yeah, so someone just asked, how can we understand loss functions? So let's just start by looking at, well, what is the definition of a loss function? So loss functions in machine learning quantify the difference between a model's prediction and the actual values. So they provide a single number representing the error. So mathematically, they are functions that map a model's prediction and the true values to a real number representing your loss or error, and smaller loss values generally indicate better model performance. So loss functions are foundational to understanding or to performing machine learning algorithms because you're always trying to minimize that distance between your true value and your predicted value. So just to visualize this a little bit better, I'm actually going to just share our whiteboard once more and just do a little sketch for all of you. So let's just look at a two-dimensional example because that's all we have access to right now. And let's say that these are our true points. So we're just gonna do something like this. And then, so this purple, this is our true points. And then now in green, this is what our model predicts. So green, this is going to be our prediction. So this is a very simplified example. If we're looking at the loss, let's do loss in orange, for example. This is the distance between your point and what's predicted. So, and then in orange, this is our loss. So there's different types of ways how you calculate loss, and I'll show you those in a moment in our slides, but I just want you to understand on a very simple level, it's the difference between what is our true value and what is the model predicted value, and then we basically calculate that distance as we go on. Got our definition here, and then we'll just discuss a couple last things about our loss. So here are 4 kind of main types of loss. So mean square error, I feel like is very commonly used. So this calculates the average of the square differences between your predicted and your actual values. So I showed you in orange that was our difference. So this one uses like the square between them. The mean absolute error calculates the average of the absolute values the absolute differences between our predicted and actual values and follows this mathematical equation over here. You also have cross entropy loss. This one I've used a lot when I've been doing machine learning algorithms, especially in clustering problems, I'd say, which makes sense here. It's commonly used for classification problems, and it measures the difference between 2 probability distributions, like the predicted and the actual, and the formula will depend on its specific application. It depends if you're looking at a binary loss versus like a multi-class problem. And lastly here, I'm showing you the hinge loss. So this often is used in support vector machines, which we've discussed already a little bit today, and it penalizes incorrect predictions and encourages a margin for separation. So you can see this formula over here is the maximum between 0 and 1 minus y times f of x. And let's see. And that is all we have for today. So just to recap everything we've gone through, so we looked first at the L2 norm versus the L0 norm, understood how to calculate them mathematically, and then we've also looked at all its applications in machine learning, when we'd use either of them. We then went into eigenvalues and eigenvectors, learned all of their applications for machine learning, as well as how to calculate them mathematically, and then looked at the loss functions. So again, for everyone who's here, I encourage you to look at my YouTube channel. I do math and machine learning. So I have very detailed, I guess, mathematical videos friendly to beginners and both experts in the field. So definitely check that out and share it with anyone else who might find that helpful. I just got a question here. Please elaborate on hinge loss formula. So this one is pretty much just used in support vector machines often. So support vector machines are often used for classifications where, say, for example, you have a bunch of data up here and you have a data over here. You're just trying to find a very good like decision boundary that's smooth that can help separate both of these parts of your data. So this type of loss penalizes incorrect predictions and encourages a margin of separation. So it's trying to like help find that best line decision barrier between your different data points. And as a result, it uses that mathematical equation. Yeah, so definitely check out our machine learning math. Again, it will be in Discord every 2 weeks. I will be presenting, or sometimes my co-lead Neil will also be presenting. And if you have any questions, please write them in our Discord channel. We really encourage like open discussions. If there's a neat paper that you've read or you're working on a certain aspect of research, please feel free to share that in our channel. Everyone's always interested to see what we're working on and always around to help each other out. So yeah, thanks again, everyone, for joining. Please let me know if you have questions. And yeah, I look forward to seeing you soon.